All right, so we're basically looking at stuff like this. See the difference between what we were doing yesterday? Yesterday, if there were separate radicals, we were multiplying or they were in a division problem. And we had this flexibility with multiplication and division where they could all be under the same radical or you could separate them and that was totally fine. You don't have that luxury with addition and subtraction. Remember we talked about this the other day, like rad 3 plus rad 2 is not equal to rad 5, okay, that we can't combine those together. So having addition or subtraction between the radicals is a little more difficult than what we were doing before, because if they're not like terms, then we can't combine them together. So something you guys can compare this to would be just like, I'm going to write this off to the side, you don't have to write this down, would be combining like terms. When you guys see an algebra problem and it has 3 plus x in it, there's not really much we can do to simplify that, okay? Whereas when it's 3 times x, we write them together as one term and that multiplication is implied. And then even if we multiply by something else like y, that still gets part of that one term and we write them all in one term but just represent each product. Here, if we try to add a y, there's still nothing that we can combine together in one term. It's still 3 separate terms. Whereas when you have something like 3x plus 2x, I know you guys are really good at this and you immediately know that that's 5x. The reason or the idea behind why that is 5x is really it's like, well, they both had an x. If I factored out the x, I would be left with 3 plus 2. I know 3 plus 2 and how to do that and combine that together. That's 5, and 5 times x is 5x. This is literally what you guys are doing when you combine like terms, but when you probably learned it the first time, they didn't maybe say it like that. They just said, oh, if you have the same like variable with the same power, you can combine them together kind of idea. The reason I want you to understand this is because what we're going to look at are things like this. If I have something like rad 3 plus 5 rad 3, these would be considered like terms, but the reason for that is you could technically factor out the rad 3 and you would be left with 1 plus 5. You know 1 plus 5. 1 plus 5 is 6. So this is 6 times rad 3 or 6 rad 3. Is that okay with everybody? But the reason I want to point it out like this is with x's, you guys are really good at it. But sometimes you guys want to add together what's in the radical. I want you to thoroughly understand you're only adding the coefficients together. Just like if it was 1x plus 5x, it would be 6x. And it's because what you're really doing is this like factoring out the thing, but we do it a lot faster by not writing it out that way, okay? If this had another rad 2 in it, we could still combine together these two through this thought process and get 6 rad 3. However, that would not be able to be combined with the rad 2, and we would just have to leave the expression like this, and it would have 2 separate terms. Is that okay with everybody for like kind of the basis of what we can combine together and what we can't with addition and subtraction? Okay. So we're going to look at a couple of problems. So for part A here, for the simplified form of this, so when you look at those, are those like terms based on how we just discussed what like terms are? Like, should we be able to add together the 2 terms in part A? Should, right? And so if you don't see that, again, I'm going to go back to like the way you don't normally do it, but to really emphasize what's happening mathematically. Notice that both terms have an a in them, and they both have a radical with a 7, a b, and a c. And if you factored that out, you would be left with 14 plus 5. 14 plus 5 you can do. That is 19. And now that 19 is being multiplied by this other thing, giving us 19a rad 7b c. Do I expect you to do the work like I just did the work every time? Absolutely not. I'm totally okay if just like right now when you see 3x plus 2x, you immediately write down 5x. I don't expect you to like factor out the x and write the 3 plus 2, okay? I'm just trying to emphasize a point about why we can and when we can't combine them together, okay? Is everybody okay with then why we could add the 14 and the 5 here? Okay, versus in this second example, they have part in common, but they're not exactly like terms. So see how there's an x underneath both the radicals, and both the radicals have an index of 5, so it's a little tempting, but that means this is what they have in common. If I factored that out, what I would have left is this. Can I combine together without changing them to decimal form and rounding and using a calculator, can I combine together 3 and the 5th root of 3? No. Okay, that means I can't simplify what I had previously. That's because these weren't like terms. They were really close, but this radical had an extra factor of 3 in the radicand. The other one didn't. It's like having x and x cubed. You guys don't add those together because they're different powers of x. They're not like terms. So this is the best we can do in this scenario. There's not really anything simpler we can do to rewrite that problem. So purpose of this first example was really just to make sure you guys understood kind of terms but with radicals, and that you could see when things might be able to combine together versus when they can't. Does everybody feel like they kind of understand when you can combine them together versus when you can't? Any questions about it? All right. So here's an application problem. You guys are going to have an application problem in the homework as well. So this is a tile, okay? And it says that the tile has congruent right triangles on it. So like here's the right triangles, in case they're a little hard to see. They've marked this angle as 90. And then it says the base is 1 foot and the height is 2 foot. So those are the lengths of the legs of the triangle. And all 4 triangles are the same. And then our job is to find the perimeter, and we're going to cross out to the nearest 1/10 of a foot. Since we're working with radicals, we're just going to keep working on it in radical form. So we're just going to leave our answer in radical form. So we want to find perimeter, which means we need to add up the edges, but we actually don't have any measurement along the edges right now. How can we get a measurement of one edge of this tile? Cooper? Yeah, are you guys okay with that? Since it's a right triangle, we have tools from geometry like the Pythagorean theorem. So this right triangle, the 2 legs are 2 and 1. So they're like the A and the B, and the hypotenuse is what we're looking for. And so 2 squared would be 4, 1 squared is 1. So added together, this would be 5. And then we would take the square root of it to finish solving this equation. And I just want to point out, because I feel like sometimes you guys think in math we change the rules. As an algebra problem, like if I presented you with this problem on a test, no picture, no word problem, just 2 squared plus 1 squared equals c squared, that problem has 2 answers. A positive rad 5 and a negative rad 5. In geometry, you kind of like forget about this a little bit. I think it's why people forget to include the plus or minus when we're solving using radicals. But the reason in geometry that we like forget about it is in geometry, most of the time we're using this, our answer is supposed to be representative of a distance, and it doesn't make sense for the distance to be negative, and that's why we're using the positive rad 5. But I just didn't want you guys to think like, oh, here she took a square root and we don't do plus or minus. But then the other times we do plus or minus, we're technically doing plus or minus all the time for the algebra portion here, but the fact is this represents a length, and so we're just assuming it can't be negative given that it's a length, okay? So I figured out this length is rad 5. Since all the triangles are congruent, then the other lengths will be rad 5 as well, okay? So what will be the perimeter of our tile? 4 rad 5, either because you're doing work like we did yesterday and just doing 4 times rad 5, or you're adding up all the sides, and because of what we talked about today, that these would all be considered like terms, this is like 1 rad 5 plus 1 rad 5 plus 1 rad 5 plus 1 rad 5, either way giving us 4 rad 5, and the units of measurement here were feet. Is this okay with everybody? All right, so looking at example 3, the simplest form of this expression. So when you look at it the way it's written right now, we have a 28. First of all, we have all square roots. So that's like a good as far as combining them together. At least they're the same kind of radical. If some are square roots and some are cube roots, there's no way those are getting combined together. So we have all square roots. But when I look at them right now, 28, 175, 63, those are different radicands underneath each radical. There's no way to combine them together the way they look right now. It looks like I would just have to leave it like that, okay? But then the question becomes, is there another way to write these radicals? So is it possible that these radicals can be written in a different format, okay? They're large numbers, right? We should at least check and break them down. So what you want to do is check each radical on its own, like you're simplifying it, to see if we could write it in a different way. So 28, and I'm going to look for perfect squares because we're talking square roots here. I know would be like 4 times 7. And I know the square root of 4, it's 2. And then 7 is not a perfect square. For 175, I'm thinking quarters here. So I know 25 goes into it because you can make like $1.75 with quarters. Okay, and it would take 7 quarters to make $1.75. So 25 times 7 would equal 175. 25 is a perfect square. 7 is not. Okay. And then 63 is at least within my realm of multiplication tables. So I know 9 times 7, and 9 is a perfect square. 7 is not. So this actually worked out pretty friendly, right? When we rewrite each of these terms, they all have a rad 7 with them, which means we can treat them all like this like term idea and combine them together. Okay? This tells me that rad 7s are what I'm adding together. Like that's part of my answer. Just like if this was 2x minus 5x plus 3x, we're not changing what x is, it's still just x, and we're adding up the coefficients. 2 minus 5 is negative 3, plus 3 is 0. So I'm getting 0 rad 7, so I guess technically we're just getting 0. Okay? So that's a very nice fancy way to write 0. Okay. All right, are we okay with that? So we'd want to check that. Things we can't combine together. If one of these wasn't a rad 7, that one would just have to be a term by itself, and we just have to be okay with the fact that our answer might have more than one term. If one of these was a cube root rather than a square root, even if it had the same number underneath the radical, we can't combine a square root and a cube root, and we'd have to be okay with writing those separately. Okay? All right, looking at example 4, we are multiplying, but we are multiplying things that have addition and subtraction within them. But look at the way it's set up. You're going to use it just like you would if you were multiplying x plus 2 times x plus 3. Anytime you have binomials, or bigger than binomials, even if it has 3 terms or 4 terms that can't be combined together and you're multiplying it by another big thing, you distribute each piece to the other factor, right? So here I'm going to distribute 1 to the 4 and to the minus 3 rad 7. So 1 times 4 is 4. And then don't confuse your multiplication with your addition and subtraction. When 1 multiplies 3 rad 7, 1 times 3 is still just 3 with a rad 7 underneath it, the radical. Okay. And then when I multiply the 2 rad 7, it's got to multiply each piece as well. What will I get when I multiply 2 rad 7 times 4? 8 rad 7. So this goes back to like the previous lesson, right? The 2 and the 4 are outside the radical. They'll multiply each other and make 8. 7 is the only thing inside the radical, so it will remain inside the radical. And when I'm doing 2 rad 7 multiplied by negative 3 rad 7, 2 times negative 3 is giving me a negative 6 as the number outside the radical. And inside the radical, remember, we're not adding here, we're multiplying. We have a 7 multiplying with another 7, which would technically be 49. But you know the square root of 49, it's 7. And negative 6 times 7 is negative 42. Is everybody okay with how I just did that multiplication? And part of the issue here is we're moving pretty quickly in this class, so we just did addition and subtraction, now we're doing multiplication. Try to keep it clear in your head which one you're doing when, so you know when you're actually multiplying the 7s together versus when it's more like a like term and you're just adding things up. And now we've just turned our multiplication problem into a large addition and subtraction problem, and we want to combine like terms. So we have a 4 and a negative 42 that would add up to negative 38. And then we have a negative 3 rad 7 plus an 8 rad 7, which would be positive 5 rad 7. And then those two terms can't be combined. So this would be the simplest form of our answer. Okay? Any questions about that multiplication process? Kind of has 2 steps to it, right? The part where we're multiplying and then the part where we're adding. So don't lose track of what you're doing in your head to make sure that you're following kind of the correct properties and not mixing them up. Okay? All right, why don't you guys try part B? Algebra 1 student and being like, the answer is 7, and they'd be like, what? Okay. All right, so when you guys multiplied it out, what cool thing kind of happened? How did you get 7 from something so complicated like this?
The positive 3 rad 2 and the negative 3 rad 2 canceled out.
Good. The positive 3 rad 2 and the negative 3 rad 2 made it so that when we multiplied it canceled out. So we got, you guys should have got something like 25 and then minus a 15 rad 2 but plus a 15 rad 2. And then a minus 18. And so these canceled out, and we were able to combine these to get the 7 you guys spoke about. We've seen this before. Okay, okay? There's a couple of places we've seen this before in our course specifically. Where have we seen this before? Cooper? Okay, so first place that we see it with our factoring patterns, this is a difference of squares. This is why something like x squared minus 4, we immediately know factors to an x minus 2 and an x plus 2. Basically just looking at the beginning and the end because the middle gets canceled out. That's why we learned that special pattern. So difference of squares, okay? There was another place in our course where something like this happened. We looked at it and it looked so complicated. It didn't even look like a real number. And then all of a sudden you finished it and you got a number like 7. Does anybody else remember what? It was still in Unit 2. What category that was with? Yeah, when we were using I. Do you guys remember? And so we'd have something with I multiplying something else times I. And like sometimes it still had I in it. So radicals and I have something very much in common. Now I is a complex number, so it's a little more extreme. However, both of them, when you square them, end up being not only real, but a very nice rational number, right? If you square something in a radical, the radical is removed and you get this nice whole number that was underneath the radical. If you square I squared becomes -1, this nice regular integer that we're used to. So you're actually going to see us do something next that's very much like what we did with I. And if you guys don't remember the vocab, this special relationship, these were called conjugates, where you had these two binomials where they had the same beginning term, the same ending term, and a different term in between. They got a special vocabulary word called conjugates. Why do these ones get that special word and not the others? Because of this beautiful way that they take something that's irrational and somehow it becomes this nice rational number based on the property that squaring parts of this turn it back into like mostly an integer with the way that we're working on it, okay? So the reason that these were important to us when we were working on I is because of our fractions and what we consider proper in mathematics and the different ways we want to write them. We always rationalize our fractions in the denominator. That means don't leave anything that is irrational in the denominator. So if you guys remember back with I, that meant if we had something like 5 over I, and it was just I, then we just multiplied it by I, right? Because then we got 5I over I squared, and I squared is just -1. And then we'd have like -5I. It might not be a whole number every time, but the goal was you didn't have anything left in the denominator that wasn't a rational real number. It's okay if it was in the numerator. How we've done that in this unit with radicals, if we've worked on, rationalizing things like this, okay? If it's a square root rather than a cube root, it's really easy because we just work on like squaring it, and I has that same property. If it just has one radical in the denominator, you guys in skill 2, you rationalize things with cube roots, fourth roots, whatever, you should be able to do those. If it has more than one term in the denominator, we're not gonna make you do fourth roots and fifth roots or even cube roots, okay? So what I want you guys to remember, if I had something like this has been on a bunch of weekly reviews. It was on your Unit 2 test, okay? How would I rationalize the denominator for this? James? Good, we multiplied by the conjugate. And if you remember why we multiplied by the conjugate, because we didn't care if there was something that was imaginary in the numerator. What we cared about was that in the denominator, we only had real rational numbers. And the conjugate, like you guys just saw, it has different parts to it, but the main thing that happens that's really nice is these parts that would have the thing I don't want, okay, in this case the I, show up in pairs that cancel each other out. And then the last place that I shows up, it shows up as a squared version, and I squared turns into -1. So this is like minus -1. So 9 minus -1 would really be 10. And so our final answer to this can all be simplified by 5, would be something like this, okay? So we kind of recall this process here that we used. So the conjugate was super useful specifically because the middle terms cancel out, and squaring I turned it into a real number. So would the conjugate be super useful if I had like 5 plus the cube root of something in the denominator? Not that useful, because does squaring a cube root make it all perfect and like a real rational number? No. But if I have a square root in the denominator, squaring it will be really nice. So our conjugates are going to be super useful because we're only going to focus on rationalizing denominators with square roots in them, not higher indexed radicals. So I'm not going to give you this in the notes and then give you like a cube root in your problems or something like this. If it's a radical by itself, yes, I can give you a cube root. You already practiced that. We already did a lesson on it. It was in Skill 2 homework. But if it has more than one term in the denominator, we're just focusing on square roots here. Is this okay with everybody? All right, so when I look at the first fraction here, 11 over 6 plus rad 3, it's not that there's anything about that fraction that's like, oh, this is simpler. It's more like it's breaking this math rule, just like in English, like where we put certain punctuation or whatever, that it's considered improper to leave something that has this radical in the denominator because that's not rational. Okay? So if I want to make it rational, I want to multiply 6 plus rad 3 by its conjugate, which is 6 minus rad 3, which is really not okay for me to just interject new things into the problem unless mathematically they don't technically change the problem. So in our equations, that's like putting something on both sides of the equations. With fractions, you can multiply something in the denominator as long as you also multiply it into the numerator, because then all we're doing really is taking this fraction and multiplying it by 1, right? This is a really weird way to write 1, but it's 1 because it's the same thing on top and bottom. And anything times 1 is still itself, even though it's going to look a little bit different, okay? So here in the numerator, I would get 66 minus 11 rad 3. And then in the denominator, I would get 36 minus 6 rad 3 plus 6 rad 3 and minus 3. So that's exactly what I wanted to happen with the conjugate, right? I wanted the parts where the radicals would still show up to cancel out, and then the other parts where there were radical to square so that there's no more radical in that expression. So then I'm getting 66 minus 11 rad 3 over 33. And then remember when we simplify this, this is very quadratic formula-ish looking, right? It doesn't have the plus or minus, but the end answer looks a lot like things you had to simplify with quadratic formula. Remember that you cannot go 63 divided by 33 is 2. You can do that, okay, if you call that 2, but you also still keep the 33 underneath the other fraction. So one way to write this answer would be like this, okay, if you separate it. If you don't separate it, then the only thing you can cancel out is a factor that works for both terms in the numerator and also is a common factor in the denominator. In this case, what would that common factor be? 11. 11 is the factor that both terms in the numerator have and the denominator. So if you factored out and canceled out an 11, you'd have 6 minus rad 3 in the numerator over 3 in the denominator. Okay. But you guys, when we were doing quadratic formula, we're often canceling this out with one of the terms and not considering it with the other, so I want to make sure we don't make that same mistake here. Okay. Is this all right with everybody? Okay, try to rationalize parts B and C. All right, so take a look at what we have on here. Does it seem okay how you guys multiplied out? Mary already gave me a couple of items in arithmetic here, so double check them to make sure that I'm good. And then again here, this idea of once you do get an answer, if one of the terms from the numerator is common with the denominator, it's okay for you to cancel that out, but you still need to consider that denominator for the second term of the fraction as well. Okay. Are there any questions on what you guys see here or how to do this? So skill 3 is basically everything before this example. So basically all of the adding, subtracting, and multiplying the radicals, but then combining the like terms is kind of the big deal. And skill 4, these 4 problems are emphasizing the rationalizing of the denominator. Okay, so 15 problems in total. That's not too many, and they're not super long. Like you saw, the longest are these, and that's these 4 right here. And so we have 15 minutes left, and I want you guys to get a good jump on your homework. You have 15 problems. You have 15 minutes to start. So hopefully you can get at least a few of those done. You can ask any questions.